I'm going to bring up my next slide. Yeah, do you want to close that one? We'll give him one more minute and then we'll close that bit.
Oh, that's fine.
In fact, you want to just close it? They can open it and come in.
I don't know, that's how we got our kids out.
This is a real experience that I had, and this isn't the exact same house, but it looks a lot like it. I did an inspection on a home, and I was there for the final. And I was working for Salt Lake County. We had asked for a load calculation. They said they would do it deferred. It never came in. You know how that whole thing goes. And the house was finished. First inspection I did was the last one. It was the final inspection. I got there. The house had a 2,100 square foot main floor, almost 2,400 square foot upper floor, and a sport court, beautiful sport court, you know, deep in the ground underneath the garage. And I asked for a load calculation per, and I quoted chapter and verse in the code, and I got this back from the contractor. And I know this gentleman and stuff. I still got a copy of his handwritten note that says exactly this, but I don't want to put it up because he's been in my classes since. But to whom it may concern, when figuring the size of an AC in Salt Lake Valley, you figure 400 to 500 square feet per ton of AC on each level of the home for maximum cooling comfort. So that means 5 ton for the main floor, 5 ton for the upper floor, and the 1,200 square foot sport court under the garage, 20 feet deep in the ground, 3 tons. So he put 13 tons. Now we were just talking about the house I built in 94, 95 at 6,200 feet. And guess what I had in it? I had a 1.5 and a 2 ton. I had 4 tons of cooling, and the house worked wonderfully because it was insulated and it was ventilated and everything was right on it. Now, I'm not saying that that's what they should have put in that house, but probably what they should have put is a 2 ton and a 2.5 ton, and they did deep air conditioning in the sport court. Let's think a little bit about that. So this is a rule of thumb that people used 30 years ago.
Insulation is different right now.
Way different, completely different. Windows, I bought my first house in 74 out there by Matt, and it had aluminum frame windows, and they just barely put double pane, but they didn't have a thermal break in the aluminum. So that window was, I got frost on the inside of the frames all the time in the wintertime. So these, it has improved, and it's really improved a lot. Many homes today come in at 1,000 square feet or even more per ton. Orientation, we've already talked about. The next one I want to ask you, so this sport court that's in the ground, I just talked about a thermal envelope, right? We have this thermal envelope. What's the thermal envelope on a sport court? They have put an insulated ceiling in it. So it had a concrete slab for the garage, and then they had, I think, an R30 ceiling. So how much heat is the sport court going to gain from through the ceiling? Maybe just a little bit, because the garage might be, say the garage gets to be 100. So the garage is 100. You have the concrete, which is not a good insulator, but then you have R30. So you have a little bit of heat that'll come through the top. What's going to come through the walls? Let's think about that sport court. The walls on the inside see whatever we want, 72 degrees or something. You might have to add a little bit of heat to it. What's on the other side of the walls? Dirt. What's the temperature of the dirt? About 50 degrees. The sport court will actually be cool. The sport court will cool itself. They'll say, oh, we're going to put some people in it. We're going to be exercising. We're going to be playing basketball. We're going to be playing racquetball. We're going to be doing all this stuff. So we're going to give up some heat.
Plug in a fan.
Plug in a fan, right? The only concern they really have is they need to ventilate it because it doesn't have any air leakage. It's all concrete. They didn't need anything in there. They needed a little bit of ventilation. And in fact, that study that DOE did, they brought out that, and you have to, this is kind of a stretch, in the summertime, if you don't insulate the basement walls, you're going to be cooler than if you insulate them because you're preventing the free cooling from the walls, taking the heat out of the basement. But I maintain you're not going to have much heat in the basement anyway, because where's it going to come from? Just like the sport court, where's the heat coming from? You don't need heat intercooling simply because it's a certain volume. You need it because where's the thermal envelope? Where's the temperature difference? Where's the heat going to be moving? Is it going to be moving it around? So anyway, this was, and I called it out, and then the homeowner called me, and I explained to him, and she said, well, I don't want to make him change it. And I said, that's fine, whatever. I just want you to be aware of it. And she called me back about 6 months later, and she says, oh, I should have made him change it. She says the air conditioners run for 5 minutes, and then they shut off. And run for 5 minutes, they shut off, and it never is comfortable. So we need to think about these things. We already talked about Thanksgiving and New Year's. We don't size our HVAC systems for that. That being said, I have worked on homes as a contractor and as a code official that the people entertain a lot. And there are people that, then you can see by the way they build their house that they're going to entertain a lot. And we're talking big dollar houses. And guess what? Those can justify that they're going to have more people in there. And I've accepted load calculations that say they're going to have 30 people because they entertain all summer. And people are in and out and everything. And that's okay if that's what the design is. But Thanksgiving and New Year's or Christmas doesn't cut it. Rules of thumb, we already talked about them, how they don't work. And it's because difference in location. So this thing, is it going to work? It won't work in Utah because why? Because every location has different design conditions. The Salt Lake Valley, different design conditions. How do we insulate it? When this house, my last house that I built, I did what they call the flash and bath. We sprayed an inch of foam, 2-6 walls, and we came in and put the fiberglass over it. What did that do? Not only did it make for a well-insulated wall, but what else did it do? Air barrier. It's air barrier. Made the house tight. I put an energy recovery ventilator in it because the house was tight. Are all houses insulated the same? No. Oh yeah, we probably ought to send that around, huh? Windows, are all windows the same? No. Orientation, we've already talked about it. Evolving codes and practices. This is the big thing, and we talked about this earlier, that we found with that study is just building practices are resulting in windows that are generally compliant and houses that are tighter than we expected. And it's just by we're changing the process of building. The framers are more and more taking their sheathing and having it start right on top of the foundation, and the sheathing covers the rim joists. They put a full sheet, they block where they need to. How did we used to build? They build everything so at every rim joist, whether it's 1 or 2 stories, you had double seams right at the locations where plates are sitting on floor decks and stuff like that. the way they're framing them now for shear and stuff, we end up with solid panels going across all these air leakage places. So just practices have changed a lot how we do things. We still have problems, but we have some problems with our roof designs and attic ventilation and building air sealing that we just talked about. So ACCA, at the first their manual says that ACCA Manual J is a simplified method. And everybody sees that word simplified and they're saying, there's nothing simple about Manual J. Well, you're right, but I taught a HVAC series for Salt Lake Community College for 4 years or 5 years, and we talked about HVAC design and load calculations. And in that class, we actually went through like the engineering steps, where we looked at each component of that envelope. We looked at the air film on the outside, we looked at the drywall, we looked at the studs, we looked at how much was wood and how much was insulation. And we went through the calculation for each wall assembly. Now that's not the simplified. What Manual J does is Manual J has done all of that core engineering calculation and says, if you build a wall with 2x4s or 2x6s, and you can put them on 16-inch centers or 24-inch centers, and we can give you a value for that wall assembly. You don't have to do all the calculations to come up with that value for that wall assembly. So it is simplified to a certain point. Manual J assumes that a standard kitchen in normal use in a typical house, you're going to figure it'll put 1,200 BTUs per hour into the house. You know, you're going to cook a little bit, your fridge is going to add some heat. If it's a bigger kitchen, we'll double that number. It's going to make some assumptions on people, you know, 230 BTUs of heat plus so much in moisture. And it's going to make some assumptions that only so many lights are going to be on at one time. And so it makes some assumptions based on our typical living in a residential building or a dwelling unit. And so some of those, because of that, we really can't use Manual J for a commercial building because that clothing store is going to have lights on all the time. You know, I mean, it's going to be a different environment. So it is simplified to a point. The fact of the matter is, it's not so simple that we should ignore it. It's important that we follow procedures for comfort. And it needs to be a room by room calculation. There are people that want to submit, they have a little simple program, and it just looks at the entire envelope and it gives you a number. And the number is accurate for the entire envelope, but we want a room by room calculation. Why? Because we want to know how much air we need to deliver from each room. That room that faces east or west, or the north room that's going to be colder, we need to know what that specific room needs. That master bedroom on the corner of the house that has 2 walls exposed, where other rooms just have 1 wall exposed, we need to know what each room needs. It might have more windows. So we just don't do a block load and then divide it up by square footage. We have to do a room by room calculation. Okay, a little more building science, and so I slapped my forehead for you. So, 1 watt is approximately 3.4 BTUs. You've heard me talk about tons of air conditioning. 12,000 BTUs per hour is equal to 1 ton of air conditioning. Why do we call it a ton of air conditioning? I'm sorry? It actually comes back from what we used to do for refrigeration years and years and years ago. Ice. 1 ton of cooling is derived from how much cooling you get out of 1 ton of ice over a 24-hour period. And then they broke it down into it. And so it's the energy to change 1 ton of ice into 1 ton of 32-degree water, just what it requires to melt the ice. And so that's what it's based on. When I first started in HVAC, then the boss says, we got a 2-ton air conditioner we're taking out to this little house out there. 2 tons, how the hell are we gonna get that 2-ton air conditioner?
It's pretty heavy, I can't pick that up.
What?
That's pretty heavy, I can't pick that
Yeah,
up.
I can't, that's 4,000 pounds. And it's in this little box. So a little more on the science. We talk about, R value is really easy to understand, right? If this is a wall assembly and we have studs and we have insulation, we can calculate the R value. If we put R19 in the wall and where studs are on 16-inch centers, the R value average for the whole wall is going to be somewhere around 15 or 16 because the studs have less R value than the insulation. And so we come up with overall R value. And we can kind of understand R is resistance. So the higher the R, the harder time heat has to move through the wall. Does that make sense? Pretty easy to understand. So that's resistance, thermal resistance. And the units, and don't let this confuse you too much, are square feet hour degrees Fahrenheit per BTU. And that just, it doesn't even make sense, even though I've spent a lot of time studying thermodynamics. They just don't read right. But when we take the inverse, where R equals 1 over U, and U equals 1 over R, so basically we flip that equation, and we have BTUs per square foot per hour per degree Fahrenheit. So the U, which we see on Windows, tells us how many BTUs go through 1 square foot every hour for every degree Fahrenheit. So if we have 50 degrees difference between inside and outside, we'll move 50 times more BTUs through it because of the 50-degree temperature difference. So for every degree Fahrenheit, every hour, we will move a certain amount of BTUs through that 1 square foot. That's the building science of heat conduction through a wall. I take that 1 square foot of wall that in my example is going to outside, and if I know the R value, the overall average R value, I just divide that into 1. I get a U factor, and I know for every degree temperature difference, I'm going to have so many BTUs. So that window that has a U factor of 0.33, if we only have 1 degree difference in temperature between inside and outside, 0.33 BTUs are going to move through it. If we have 10 degrees temperature difference, 3.3 BTUs will go through the window, and if we have 100 degrees, so it's just a number that tells us how much heat will go through 1 square foot, depending on the temperature difference.
And that's why the U factor, the lower the number, the better.
That's why the lower the number, the better. So I just said 0.33 window. So what's the R value of that 0.33 window? I know I'm asking you to do some math in your head. 1 divided by 0.33.
It's like 3.
3, right? Yeah, 1/3 divided in 3, divided into 1 is 3, right?
Otherwise they suck.
Huh?
Windows suck.
Yeah, windows suck.
Yeah,
And that's a good window. What's an aluminum frame single pane window?
45. So about R1.
It's R1 to R1.2. Excuse me, the U is 1 to 1.2. So the R is less than 1. A triple pane window is usually around 0.5. I mean, it's usually around R5. It's 0.2 for the U factor. So you pay the money, but you get up to R5. So windows our weak link. But do we not want to have windows? No.
Well, it's like you said, we're evolving to these homes that are nothing but a solid glass wall in certain areas of the home that are 23 feet high because of views.
Yep. And we need to make sure we account for them. Down here, it's really popular for high-end homes that have a view to put in budded glass. Do you see some of that?
No, we have a developer that wants to start doing that.
And there is only one way, and we're not going to go into big detail, but you know what budded glass is? It's half-inch thick glass that they just bud it together and put a little bead of sealer between them. Terrible thermal performance. But there is actually a way you can get it. If you have a limited amount, you can actually get it to comply with the code, but you're going to have to build the rest of the building really, really well, and you're going to have to do what we call a HERS rating or an energy rating index calculation to get it compliant, because you can't get it to, res check won't let you put it in a window like that, period. Anyway, that's the science, and I know it might appear confusing, but it's really pretty straightforward. You know, so much heat will go through every square foot. We just got to identify what the square foot is. So we have this formula, and it takes that very thing. We take the U and the temperature difference. You see the delta symbol? That's the difference in temperature between inside and outside. So if I know the area, the U factor, and the delta T, I can do that calculation. And that's what I did by hand back when I started doing it. And what manual J gives us, and it still gives us if you go to the book, it actually gives us what we call a heat transfer multiplier, which is U times delta T. So if you have the U and the delta T, all you need is the area and we can get the load. So it actually gives us tables that we look it up. It tells you if you have this window and 50 degrees temperature difference, your heat transfer multiplier, or your U times your delta T, is this number. You just multiply it by the area and you have the heat that's going to go through that whole wall. And we got an example here that I'll show you in just a second. Spend a little time if you want to on that. And you know, for summertime, I'm just going to make one comment and then we're going to leave this one alone. In the summertime, Manual J and the software all makes an adjustment for solar gain, because depending on the color of the building and everything, the software at Manual J does adjust it to take into account. I have a dark siding on a house. It's going to absorb the sun, and what the inside sees is a hotter temperature on the outside. Does that make sense? Or a dark roof, it's going to see that dark temperature. Those down here, you build a commercial building down here, you're supposed to put a white roof on it to reflect the heat away in the energy code. So I just wanted to go, if you want to get this out, or you can just watch what I've got here, but you have this same thing right there. Let's talk real quick about, I've been talking about this delta T, this temperature difference between inside and outside. On the load calculation, one of the first things you have to do, and this is a load that was done for a house, a guy I know that does them all the time, and so I've whited out everything that identifies which house it was. But this is a real live load. The design information that he selected was outside temperature for winter was 7 degrees and inside temperature was 97. And the software will actually pick it up, but you have tables in the book that give you what numbers are designed for. And this is where we've had a lot of arguments. The first thing the code official does is he goes to this and sees what number it is. And then he goes to his Manual J and he says, and he sees that Salt Lake says 95. And someone put 97 and he sends it back and says, no, you can't use 90. 97, you have to use 95. And then he'll say, well, well, I'll just pick the closest location. Well, great, but how about we use a little bit of common sense here? What these numbers are, and then winter times 7, Salt Lake design is 11 or 12 or something, and it changes. This is based on historical data. So if this is based on historical data, do we need to think a little bit, what is our climate? What are our conditions doing right now? Maybe. We don't want to do an average of 30 years. We might need to raise it a few degrees. What these numbers mean is that in the winter time, this number that comes out of Manual J means that 99% of the time, it will be 7 degrees or warmer in the winter time. 1% of the time in the summertime, it will exceed the design, the summer design that's in the book. Do we go, we had like 14 days at 100 degrees in Salt Lake this year, over 100 degrees. Probably more than 1% of the time we were above 100. Now, don't get too concerned yet, but typically, how many hours a day are we over 100? 3 or 4. We take summer months and divide it out, and we're still allowed to be over, for a certain number of days. And the same thing with cold. We'll go years and years and years without going below 0 in Salt Lake, but then every so often we'll go, and we're below 0, and we're there for a week, during an inversion. The first thought, and everybody's thinking, well, hell, if I size my furnace based on this, what happens when we go below 0?
Furnaces work hard.
Your furnace runs a little bit longer, but when you do a load, if I look at this load calculation, I flip to the second sheet, it says the heating load is 29,623 BTUs. It's the second column. So that 29,000 is the heating and the 17,000 is the cooling load, based on these two temperatures right here. So do I call the supply house and say I need a 29,623 BTU furnace? Yeah. We pick the next size, right? And the next size is always going to give you enough cushion to get you through those 1% events when you're colder or hotter than your design condition. So don't get hung up on, what our design conditions are.
Now, just a quick question on that. Like, what is a good range? Because we know, so for us, yes, Salt Lake is, say, 11. We'll go for ranges like 8 to 14, somewhere in there. But, what warrants a comment, I guess, is a good question for that.
Okay, let me get to 2 more slides, and we're going to really cover that in detail.
Okay.
And what I'm really going to tell you is you got to kind of need to decide yourself. I'm going to suggest, I think everybody in here is a code official of some type. Please do not send a plan back and say, you're 1 degree off, redo it. Or 2 degrees. You know what? The bill went through the legislature this year that's trying to limit what we can do with load calculations. And part of it's because we got a little bit too anal on what we were trying to do and what we were focusing on. And this is one of the things that created some problems. The 21 code actually, you know how in chapter 3 you have all these design conditions, these design parameters? Mm-hmm. They've thrown this table in, telling the jurisdiction where you're located, spend a little time and figure out what you want your design conditions in Midway, right?
Yep.
And if you want to, look at current history, the last 3 or 4 years, and you want to adjust a few degrees and then give them a range, I think that's what we should do. We spend way too much energy focusing on this one. Don't let them get away with ridiculous. Did you call me on the one, or maybe it was before you were there? You're still in Midway, aren't you?
No.
Oh, you're not?
I'm in Heber, Wasatch County.
Oh. Someone from Midway called me and said, someone turned in a load calculation for 105 in the summertime. I looked up, Midway's never hit 100.
Nope.
Ever.
It's more, the thing that I ran into is they wanted to do the higher temperatures for the winter design And we're at a 0.
Yeah.
We get colder,
Yeah.
so.
So anyway, don't let them do something ridiculous, but, so anyway, it gives us, the 21 code wants you to kind of put this to bed and decide for your jurisdiction what you're gonna do. Now here's getting back to, was it Matt that asked, or whoever, which one? Oh, I can't see your name. Aaron. Sorry, I can't remember names. Jody just came up to me and said, hey, you remember that class that I attended 2 years ago? I need to get my CEUs on it. Which class, Jody? Jeez. I can't remember what class, I can't remember everybody's name that's in them, so maybe it's because there's so much up here that I can't find it, right? Okay, so Salt Lake City is at the airport. This is from Manual J. And these are the numbers, and they might have changed. Since I did that slide, I think the last version might have changed this to 95. So here's Salt Lake Airport up here with the star. What's this right here?
Great Salt Lake.
Is this a good place to pick a design condition for the Salt Lake Valley?
Oh,
It's a horrible place, isn't it? What's the Great Salt Lake going to do? It's got to moderate both ends. We're cooler in the summer because we have the evaporation off the lake, and we're warmer in the winter because we have a warm lake that doesn't ever freeze, that's releasing some heat from the ground up through the conductive water. And so the Salt Lake Airport's the very worst thing. I live down here. I freeze 4 to 7 days before the airport ever freezes every fall. You know, I don't pay attention to the weather on when it's going to freeze. You know, when they say it's going to be down to 36 or 37, if I want to protect something, I'm protecting it because it's going to freeze at my house. And I get hotter because my location. Let's go to the extreme. So I've heard several say, I just picked the closest place to my location, and that's the design conditions I use. When I was at the county, they built and we inspected. We had to ride the big tram up to inspect the Snowbird Summit. And I don't know if anybody's ever been up there at the top of the tram, that new building they built, 20-something thousand square foot building, gorgeous building. That wasn't climate zone 5 really, even though the code says it's Salt Lake County, so it's climate zone 5. And it's close to Salt Lake Airport, so it's designed this. No, I went and did some calculations based on the heating degree days, and design should be minus 15 and 78. Just because it has a number in the book, there's nothing in the book that says you have to use the closest location.
It's common sense.
Use some common sense, determine the temperature that you should design for. So Salt Lake Valley, if they're in the valley, I don't care if they design for 5 degrees, and I don't care if they design for 100 degrees. It's just not that big a difference. It just doesn't change that much. What does it do? It changes that temperature difference by 3, 4, or 5 degrees. And it's just going to change. Instead of 33 BTUs going through that window, it's going to be 36 or 37 or 38 BTUs that go through the window. Let's focus on stuff that really matters, like getting the air to the room where it needs to go. Yeah, that's a big difference. Now, so here's Salt Lake, and this has a little more information. I'm going to bring it up now. We'll talk a little bit more later. It has a design grains at 45% relative humidity. If you look at this, and I'm going to back up. Moisture difference, grains per pound, minus 25 grains. Okay, when we design an air conditioning system, the manufacturer's tables give us, and Manual J gives us 45% relative humidity, 50 and 55% relative humidity. Those are the three humidity levels that we're supposed to design to. There's 7,000 grains in a pound of water. What the grains of moisture is telling us is how many grains of moisture do we have in 1 pound of air. So it's just a relative number. Don't worry a lot about it. Just remember that when it says negative 25 grains, that means the air is drier than 45% relative humidity by 25 grains per pound of air. So we should always in Utah have a negative grains of moisture, and people might try to cheat by picking a different moisture level. And if you see anything that isn't a negative number in Utah, they're trying to get extra air conditioning capacity by messing with the moisture level in our air.
That's what I dealt with the most.
Yeah. Yeah, they're playing games because they want a bigger air conditioner. They want a bigger air conditioner. And we're drier. We're never 45% relative humidity in our house in the summertime. It might get humid, a thunderstorm rolls through and the humidity goes up. As soon as it clears off and the sun comes out, we're back at 25 or 30% relative humidity. Huh?
Right, or Texas.
Yeah. Biloxi, Mississippi. I spent a year in Biloxi, Mississippi, radar school in the Air Force.
98%.
Houston. I'm talking about 8 times in Houston, talking about humid. So, design conditions. Here's St. George. I don't care down here if someone's designs for 105. I really don't. What they need to be worried more about is how's their duct system? Do they have it buried in the insulation? Is it airtight? Maybe getting the air handler out of the attic or everything. And see, they're dry. And 21, I think that's actually probably a low number. I don't think they spend that much time down close to 21. But anyway, always consider the specific location, not one that is close or similar. Don't get hung up on a few degrees. I just threw in a few things. And I think this is an error. I sent an email to ACCA to get a clarification. Version 1.2, that I don't have a version with me, has Provo at 96, St. George at 101, Salt Lake at 94. In the new version, Provo went to 91, and I think it's a typo. They dropped 5 degrees where everybody else went up a degree or a few degrees. And that's the number that a lot of people have really spent a lot of time worrying about. That Provo, they're only supposed to design for 91. So anything in close to, and guess what? The Provo airport's kind of close to the lake down there. So, and this is what the table looks like in Manual J, Table 1A. And this is all they have for Utah. We have lots of places that aren't there. South Jordan, where I live, isn't there. The 15 other cities in the Salt Lake Valley aren't there. And so we just need to just be a little careful. Let's not get hung up on that one. I gave you a sheet, and we're not going to have time to go through it all, but I gave you 3 sheets like this. And if you want, people ask me all the time, do you have a guide? Do you have a guide that I can look at? And these 3 sheets that ACCA puts out, and if you want a PDF, rather than trying to photocopy these, let me know, or you can go to their website and get them. But this first sheet gives you a lot of good information on comfort, problems with oversizing, reasons people oversize, how to verify it, and talks about the things that we need to be looking at. And I like this thing here. things that we really need to focus on. Yeah, we need to focus on a reasonable design temperature. Our windows, our ducts, and our ceilings under attics. Those are big, those make a big impact. These make a little bit less impact. Our small skylights, infiltration, and ventilation. And floor make less difference. Walls, as long as you get the wall right. A little change from like R13 to R15 really doesn't make that much difference. And internal gains make a little bit. But anyway, this is a good guide that kind of goes through some of the things we've discussed, but what's really nice is on the back side, it gives you a checklist. And if you want to know how to review one of these, and I'm going to tell you real quick, you want to look at your indoor and outdoor design temperatures. And we've already had that discussion. We want to see that the U values and solar heat gain for the windows are reasonably accurate. I don't worry a lot about shading adjustments. And they're talking about curtains, drapes, and all those types of things. When I did an HVAC load for systems I was installing, I assumed that they probably weren't going to always close the blinds. So I assumed them without blinds. And if it was a big house with a lot of glass that I had to put in the blinds to get it to work, I would caution the people. When the sun hits this west glass, if you don't close your blinds, it's not going to cool. But as a code official, don't be asking them to include the blinds in your load calculation. We're just nitpicking at that point. Yeah, you can adjust for overhangs. The areas need to be right, the exposure direction or the orientation. Skylights, how many see skylights? I really don't, unless the house has a bunch of skylights, I really don't spend a lot of time on that one. Doors are not a big deal. Most of the doors are really good. Check the wall insulation, check the ceiling insulation, check the floor insulation. They should adjust for the infiltration, but there's just the checklist of all the things they should be looking at. And ducts are a big one. Huge.
Real quick on total wall area, this is something we see a lot where they'll show walls on the RJ worksheet or whatever that are, off. And we understand, it's not going to be calculated perfectly according to the plans, but what's a good range for a wall? I'm like, if it's 100 square feet off or something like that, is it a really
10%.
big deal, or
10%.
about 10%?
10, 12%. RightSoft, actually how it works now, and I'm not real familiar with doing it, but what RightSoft has them do is they actually draw the house.
Right.
They draw the house, and RightSoft won't let them put in an inch.
Right, it does 6-inch increments.
It does 6 inch
12-inch
increments, and so it's going to be off a little
Right.
bit with that. But when I review one, I pick a room, like I'll go to the master bedroom, and I'll look at the orientation, and then I'll look at the wall area, and if it's in 10% or so, I don't even worry about it. And I just check 1 or 2 rooms to see if the areas look okay. And if I look at 2 or 3 and they don't look right, then I say, hey, your numbers don't match.
Because usually we'll look at the entire house and then maybe go down to the rooms below that. But, also if you try to use a general blanket ceiling, but if it's vaulted, that's going to have a difference as well. So.
And RightSoft can account for vaults and everything.
Right.
Yeah. And so can Ely and the others.
Yeah, just comparing with the plans versus how they're drawing, and I know our numbers are going to be different.
Yeah, there's going to be a little bit, but again, it doesn't make a huge difference. And so, what it really does, and here, this is really the nuts and bolts of the whole thing. We get a relatively accurate load calculation within 10 or 15%, and then we get a duct design based on that load calculation. And you're going to get sick of me saying that because this is all we talk about. Then the key thing is building a duct system with the right components and the right filters so you get the air in those places. So if it's off a little bit, it's off the same in every room. So proportionally, we're going to be feeding the amount of air we need to each room. You see what I'm saying? If you're off 10% on all the windows, it's still going to take I put the right proportion of the air in that room. Right? So, yeah, and the same thing with res check. You know, the res check and the load calculation numbers should be, areas should be fairly close. Now, you gotta be careful if it's net or gross area. Res check, you put in gross area, that's the math.
Yeah, and that's usually what we look at, because windows we're pretty on the line with, you know, if it's off by 1, we're not as concerned, but wall areas, we see a lot more variation sometimes.
Yeah. Good guide, like what we've talked about today, we could spend a whole day going into more depth, and so we're gonna jump through. Okay, why is heating is not as critical as air conditioning? The sizing helps control moisture and the cycle rate. And I do want to add that everything that we're looking at here, the energy code, the ACCA standards are based on like 85 to 90% of the country has humidity by population, not by land area, but by population. The vast majority of the people in this country live in a humid climate. The manufacturers manufacture for humid climates. They charts and the engineering data is based on humid climates. And it was just this last printing of Manual J that several of us that are from high and dry climates participated in the committee and said, hey, you're not all high, we're not all humid, we're high and dry, and we need to design different than humidity. And so I am going to talk about moisture control simply because we do sometimes, depending on our lifestyle, even though it's dry outside, we need to control humidity. In fact, we all need to control humidity in our bathrooms, right? Big time. I'm doing a master bathroom remodel right now. Moving everything, you know, got it right out, and had a jetted tub in the corner. And now I didn't have a vapor barrier anywhere, but guess what I had? The jetted tub leveled down. When I took out the jetted tub, I had signs of moisture all the way around the entire space, you know, below the jetted tub line, because there was no drywall or anything going down there. It was just insulation. The moisture could easily get in there and condense on the cold OSB. And this is a house that leaks, that it should dry, you know what I mean? But what's the problem? Previous owners and ourselves didn't run the fan when you showered because the thing is so noisy that drives you crazy, right? What's my new fan gonna be?
High efficiency.
Huh?
High efficiency.
The best part is the code says if you have an openable window, you don't need it, and we know everybody opens their window to
Yeah.
shower.
Yeah. When the humidity goes up, the building signs, the psychrometrics say, with high humidities, higher humidities, you get moisture condensing. I mean, as a kid back in the early 60s, we'd sleep outside all the time. You know, I don't know if any of you did as a kid. We always slept out in the sleeping bag on the lawn, and some mornings you had dew and some you didn't. And you're going, why do we got dew? It's because the humidity and the conditions are just right that it condenses. Well, the humidity and the conditions are just right when you load a bathroom full of steam from a shower. It's going to condense in your walls. And over your tub where there's no insulation down at the bottom of the trusses and all these things. And so we do have to control moisture. Even if we're in a dry climate. If you oversize it, how does an air conditioner remove moisture? The same way as, you know, I have a little ice in here and I got a little bit of condensation here, right? Out of our dry air. Well, it's not as dry because it rains, but an air conditioner removes moisture because the cooling coil is cold, the moisture condenses on it, drains down, goes down the drain. That's how we remove moisture. If the air conditioner is not running because it's so oversized it just runs for 5 minutes and shuts off, how much moisture is it remove?
Not much.
Hardly any. So in the humid climates, they need that thing running all the time, and then they add dehumidifiers to take more moisture out.
Can I ask a question a little off topic?
Sure.
The condensate that's coming off of the furnace and the AC, is that bad for cast iron piping?
The condensate coming off furnaces and ACs is bad for cast iron. Condensate coming off your furnace is bad for cast iron. The condensate coming off an air conditioner is just this. The condensate coming off your furnace is not moisture out of your air. What's natural gas? I think it's CH4. It's carbon and hydrogen. You burn a hydrocarbon, and if you burn it perfectly, you get two byproducts. Carbon dioxide, which catches some of the carbon and the oxygen out of the air. What does a hydrogen bond with and form? H2O. So any hydrocarbon that you burn creates water. So that's a condensate. It comes from the combustion process.
Right.
But we have, in our natural gas, we have sulfurs to make it smell. And it's not 100% pure carbon and hydrogen. And so if we have some chlorines in it, we're going to get hydrochloric. If we have some sulfur in it, we're going to get sulfuric. And so it's acidic. And so if you're running it into a cast iron system, and not a lot of other water coming through, because detergents and stuff are base and will neutralize it. But big boilers and stuff in commercial buildings, because most of those are cast iron, they put acid neutralizers on the condensate, and so the condensate goes into that and neutralizes it, and then it goes down the drain. If it's plastic, you don't need to worry about it. And it's not like we're putting all this acid in the sewer treatment plant, because we're putting so much other stuff in there to neutralize that acid. Where it's not an issue. If you run that condensate on the furnace, if you see it running across the floor, what does it do? It etches the concrete. It rusts the furnace if it leaks in the furnace. So it's an acid. It's a little more acidic than orange juice, is my understanding. So, okay, I get asked a quick question. So a 2.5 ton air conditioner, 30,000 BTUs, a 5 ton air conditioner, 60,000 BTUs. If you run a 5 ton air conditioner for 3 hours versus a 2.5 ton for 6 hours, let me back up and rephrase this so it makes a little more sense. I have a 5 ton air conditioner that cycles on and off. I have a 3 ton that runs, a 2.5 ton that runs continuous. So this produces, by cycling on the thermostat, we get the same number of BTUs because it's only on half the time, right? So this will produce every hour. This will produce, by cycling 3 times an hour, it's going to produce every hour 2.5 tons because it's only running half the time. This one produces 2.5 tons every hour, but it's running all the time. So at 6 hours, they produce the same amount of cooling. Which would cost the most? 5
5
tons.
tons,
Produce the same amount of cooling, shouldn't it be the same energy?
because it's off and on.
It's off and on, it has to start and stop and start and stop.
Start features, the big loss, that's one that has to use a startup capacitor just to make that block rotor turn.
Yeah, just to get you gotta get it started. Then if you have a vehicle that has the little MPG gauge on it, my truck, if I put it on the right setting, it tells me my instantaneous mileage, and then it gives me my average and everything. And you pay attention to it as you start off from a stop sign or a stoplight. I mean, my MPG is like 1, 2, 3, 4, and then I get up to speed, and then it will come up in at 80 miles an hour. It's amazing. At 80 miles an hour, I get about 18 to 19, but at 65 miles an hour, I get 20, 23. Why? Because of the wind and everything. But the big thing is bringing it up and accelerating, getting that mass moving. Well, the same thing happens in your compressor. Here's, and some of you have seen this before, here's a label off a Tempstar air conditioner. And who just said lock rotor? When an AC motor, a standard AC motor is sitting, not moving, when you first put current to it, put power to it, it draws what we call lock rotor amps. And until it comes up to speed, it's going to draw a lot of amperage until it gets up to speed. So this unit, which is a 3-ton air conditioner, when you first put the power to it, it draws lock rotor amps. Can anybody see that? 79 amps. If it's a 5-ton, it's like 149 or 150 amps, right? And that's why when your air conditioner starts, your lights dim. I have the same thing. I have a big air compressor sitting out in my garage with a 5-horse motor on it. It dims my lights more in my air conditioner because it's a bigger motor than my air conditioner when it starts.
That's why we're allowed to oversize when we do electrical motors, 125%.
Yeah,
That's why they want to, yeah, for that long.
We have to
for startup. And that's why the power company says, please, please, please let us put this device on your air conditioner, a cool keeper. And what is it? And what do?
Shut it down.
They shut off, they know, and I mean, there's no secret. They know that we have put in so many oversized air conditioners. In the middle of the summer, we have all these great big air conditioners. Every instant, there's a whole bunch of them trying to start. And we're putting this huge load on the grid, trying to start these great big air conditioners. And it increases, they're trying to provide 5 times more power than they really need to provide because of all these grossly oversized air conditioners.
Well, that program come out about the same time everyone in Utah, in theory, started enforcing manual J&D. And that program kind of went away, didn't it?
I think it's still out there, but
Is it?
it helped. But that's, so what do? They take and they shed some load. So they put this thing on your thing, and when they'll sell you the power all the time when they can provide it. When it's not, but when it's really hot and we have all these things doing it, what they want to do, and it's smart, they want to shut your air conditioner off and let your house heat up 2 or 3 degrees. So they shut it off for 20, 30, or 40 minutes, and then they let them come in. So guess what? They're running, and they're not having to deal with so many starts and stops. And so at running, this unit is compressor 16.7 at full load, hottest day of the year, versus 79. So they can handle this.
You can even upgrade your starter capacitor and have less of that power.
To
back
take some of that out.
Information where it's not so loading on.
Yeah.
Funky.
Commercial jobs, you see all these, here's what's that, you see freak drives, right? Variable frequency drives. They take it away and they make your motors work better and everything. The bath fan that I'm putting in my bathroom, I already ordered it. It's one of those Panasonics with all the DC inverter drive. I put my amp probe on it. You know, I got a box, you know, I'm a nerd. Got the box out, put a cord on it, you know, plugged it in. My amp probe won't measure low enough to even measure the current that it's drawing. And I left it on at 100 CFM sitting on the island in the kitchen. My wife says, "What are you doing?" I says, "I just want to see how loud it was." "Well, turn it on." She says, "It's been running. You've walked by it 4 times. Can't hear it."
Your condensers have gotten better over the last 20 years. Old condensers were always 40 amp, 2 pole circuits.
Yeah.
And
Yeah.
even small ones, and they're just not pulling the same.
Yeah, they've improved them a lot. These are all good reasons why we want to size it right. The mini splits and the multi splits and everything, they all are inverter. They start soft and they,
Did I tell you about my house, Brent? I went from 125,000 BTU 80% furnace to a 60,000 BTU 2-stage, and that second stage rarely kicks on.
yeah. You cut your furnace in half with a 2-stage and it's still bigger than you need.
Yeah, it still rarely kicks on.
Yeah.
2-stage.
Yeah. You have comments?
Well, it's kind of an interesting thing in California because of the mandatory photovoltaics. The power companies are in trouble. They call it the duck, but the duck is getting fat in the middle, the 24-hour power curve. They're getting too much power in the afternoon. They're actually
Back into their system.
back into their system. So the last 3 years, they've actually had to pay Arizona to take their power. And so they're changing their philosophy now. They're trying to get people to turn their air conditioners on in the middle of the day and turn them off because everybody gets home like at 6.
Yeah.
And get the house cooled down when they have a lot of power. And the solar panels are working.
Yeah. Yeah, solar panels
It's
and all these things are really changing the
Change the
system.
dynamics.
They're changing the dynamic of it. Yeah, my son lives in California, my brother lives in California, and right now they charge them more in the afternoon when it's hot for
Yeah.
power. And he has Teslas and he sets them to charge in the middle of the night because his power is a lot cheaper in the middle of the night. Fenestration windows. I don't know if you can see this very well, but can anybody read what the U factor is right here? 0.15. 0.15. Is that a good U factor? It's a door. But that's fenestration, a door. If you take one of those the current, you buy them everywhere. They're metal or fiberglass inside and out, and they have the little wood thermal break running around the edges. If it doesn't have a window in it, it's going to be around a 0.15 U factor. So what's that? That's a little bit better than R6. So that's a pretty good door. Here's a window, and this is quite typical of a double coat Lowy window. 0.28. 10 years ago, you could not buy a double pane Lowy window that was 0.28. They were struggling. They were struggling to get down to 3.3. There were 3.5 and 3.4, and we had to do these area weighted calculations because some of them were 3.7s and everything, but the technology has improved, and
So that's what they're changing the gases inside the window?
to get down below the 3.3, they put a second coating, and they put it on the inside pane of glass, and they'll even have a sticker that says, "Don't use a razor blade," because there's the original design is the coating on the inside surface of the outer pane of glass, and now they're putting a second coating on it, and that's where they're getting the improvement. And yeah, that's an Amsco window. Solar heat gain coefficient 0.3. What's that 0.3 mean?
That's how much heat is
It lets 30% of the radiant heat of the sun through that window. It reflects 70% of it out. So if you have new windows with a low solar heat gain coefficient, that west glass is not near as.
This might be a stupid question, but while we're on that fenestration subject, why do we put vents over windows if we're just going to lose the heat out the window?
That's heat loss.
Say that again?
If we're losing that much heat out the window or cooling out of the
So much heat
window,
coming in.
why do we have our vents directly over a window or under it?
Oh, our supply airs and stuff. Why is our supply air discharged? Well, this comes back when they first started doing forced air heating. If you're in an old house, a lot of them, they put the returns at the outside and they put the supplies on the walls in the middle. Then it was hot in the middle of the house and it was always cold at the outside. The windows were so poor that you wanted the heat there to kind of give you a little bit of a buffer. You blew the heat up over it. Yeah,
It's like Walmart's there, and that's still your weakest spot in the room.
yeah. If anybody, I know with most of us have lived in a house or had a house. My house that I've been in continuous remodel since I bought it back in 2005. Changed out all the windows except 2 windows because they were on the end of the house. There were 2 small windows, one in my bedroom and one in my master bathroom. And they're aluminum double frame windows. I changed everything else out, but I was going to do some stuff on the outside and I didn't want to change them. And if you sat by one of those windows, you thought you had a draft. And my wife says, those windows are really leaking. And I said, the windows aren't leaking. When we have a cold single pane window or a double pane window that's aluminum frame and kind of a junky window, the air from inside the house that's close to the window is going to do what? It's going to cool. So it's going to drop. So you're going to get this convective flow and it feels like a draft, and it is a draft. And it's just, so we put the heat out there to try to
That makes sense.
temper that
I never could
or
figure it
minimize
out.
that. Yeah. But you know what? As well as we are insulated, even with an R3 window, it's not that big a deal. Down here, they don't need to take them all the way to the outside. If you put the right register on it, you can throw it across the room. I'm sure you've seen apartments that they don't take the supplies all the way to the windows. You can throw 10 or 12 feet with the right register across the room, and it'll work just fine. And we don't have the cold outside walls. Going to just double pane glass really makes a difference on feeling that cold. So let's talk about glass again, and we're doing this really so you understand what changes the load calculation. They want to build homes with a butt of glass, just like this right here. Let's see. So most of the windows we have now have an IGU, an insulated glass unit. So they take 2 panes of glass, they have a spacer, they might put argon in or whatever, but they evacuate it, they put the coatings on it, and they manufacture the sealed unit. Commercial windows, same thing. They bring them out and put them in the site-built frames. But they all have this double pane IGU. Going to Manual J, I pulled out how the glass performs. And a 1/4 inch pane of glass has an R of 0.046. Now, I didn't do the math, but that's a pretty high U. That's terrible. If the glass is a 1/2 inch thick, it goes up to 0.0992 from 4.6, so it just doubles. It's just a proportional relationship, and if it's 1 inch thick, we're up to 0.185. So why are we making these IGUs? Because the air film that we capture inside there, we don't want the window leaking it, but we want that sealed air gap in there. Let me jump down to here. The air space has almost an R1. And so by adding that airspace, we drastically improve the performance of this. Because 2 panes of glass is still only just barely, not quite an R, 0.1, a 1/10 of an R value. But by adding an airspace, we almost double it. And then we have what we call air films. Has anybody ever flown in a small plane? If you fly in a small plane and it's got a little dust on the wing, write something in the dust and fly someplace at 180 or 200 miles an hour, and is it still going to be there? If you have a dirty car that has some dust on it and you ride on it with your finger and you drive at 80 miles an hour, there's still some dust clinging to the surface, isn't there? Well, air by its nature on a building, we have a little air film, this outside wall, that kind of clings to the wall. And on the inside, it's always there, and it has a certain amount of R value, and there's one on the outside that has a certain amount of R value. It goes down on the outside because of air movement. But those 2 air films together have an R of about 0.75. So on a window, we account for the glass, we account for the coatings on the glass, we account for the air of the glass, and we account for the air films. And that's how they come up with the U factor for it. When we have a wall, then we account for all the stuff in the wall. And we'll go a little bit deeper on that. Bottom line, if they want to use a solid pane of glass, it's going to be, with the air films, it still sucks. It's still horrible. And the only way they can get away with it is limiting it and do what we call the energy rating index. And if you send me an email, I can give you some more information on that, because it's happened down here quite a bit.
Yeah, it's a developer from here. It's developing over there.
And there's people, I don't know if you have HERS raters over there, but there's HERS raters here that can do the HERS rating to get that to comply. My point here is glazing is a weak link, and we need to be aware of what they're putting in. So this label should come on every window that's manufactured. It's going to have a U factor, it's going to have a solar heat gain coefficient, it's going to have a VT. That's how much of the light gets through the window. The more coating and stuff, the more we reduce the lighting. So when we get in commercial jobs, we start worrying about how much lighting are we reducing. This label should be on every manufactured window so you can look at it. And it should be NFRC certified to those values. So when someone turns in a res check that's really crappy low, well, exaggerated with a low U factor, I've had them turned in, one of them that said they had a 0.05 U factor. Yeah, an R20 window. Yeah, give me a spec on that window.
And then tell me where to buy it.
Yeah.
What if you go through the house and you see those stickers and you have the same window and then right next to it, the stickers don't match?
It's generally because one's operable and one isn't. If it's a fixed window, it's going to be a little bit better or a little worse depending on the frame material.
That exact same window.
Sometimes they think we have the wrong window for the wrong side of the house.
I don't know. The ones I've noticed are generally, one's a casement, one's a slider, one's fixed, one's, but it's what, 1/100th or 2/100th or something. So it's, this is tenths, this is hundredths, but.
Crappiest stuff you got on your wall.
What?
It's crappiest thing on the wall.
It's crappiest thing on the wall. Yep. So let's look at how this changes. Single clear glass and an aluminum frame, U factor is going to be around 1.27. So the R is going to be 0.8 or something like that, 0.7. If it's 5 degrees outside, 70 degrees inside, that's a 65-degree temperature difference, right? 5 off of 70, that's our difference between it. To get our heat transfer multiplier, we take the 1.27 times it by the 65. So that single pane clear window will lose 82.5 BTUs per square foot. BTUs per hour per square foot. So every hour we lose that much. If we have one 5x5 window, it's 2,063 some odd BTUs per hour going through that one window. So if we have 300 square foot of window in a house, which is a good number to use for the calculation, our aluminum clear single pane window, we have 25,000 BTUs of loss through the windows. The same house with clear glass, vinyl clear, 9,800 BTUs per hour, and with low E double glass, we're going to be around 6,000 BTUs per hour. Is there a reason why rules of thumb don't work? That's a big difference, isn't it? That's more through the windows than a 1,200 square foot house even has today. This one here has a total square footage of 3,200 square feet, and the whole house is only 29,000 BTUs of loss. You put single pane windows in it, you'd double it. Heat gain through the glass, we talked about this a little bit already. That's the solar heat gain coefficient. How much heat of that radiant heat gets through the glass? Varies by month, time of day, direction windows are facing, number of panes, and type of shading. Now let's think about that. Remember right at first I talked about if you do a perfect load calculation, is your house always going to be comfortable? No. And this is one of the big reasons. Every single day throughout the summer, at 2 o'clock in the afternoon, the sun is in a slightly different location. In fact, it's all year long. The sun's always moving, it's in a slightly different location. Don't you notice when you're driving throughout fall and winter and summer that you're always flipping your visor to the side or something because the sun's in a different place, because it's changing in the horizons? Well, your house every minute of the day in the summertime is experiencing the sun on the house a little bit differently. It's going to be hitting windows different all the time. And so the load isn't going to make it perfect. We're always going to have this variable solar heat gain coefficient on our house every day. And if we want, I've been involved in some, as an expert witness for some litigation where people are expecting the house to stay exactly one temperature all the time. But they only want to pay for one furnace with one thermostat, and they don't, and they whine because their kitchen gets hot when they cook. Imagine that, your house gets hot when you cook. Huh. So our solar heat gain coefficient, that number right there means 32% gets in, 68% is reflected out. Triple glazed window, here's one that has a 0.21 for the U factor and a 0.20 for solar heat gain coefficient. So what if you build a passive house that you want the heat to come in through the south glass in the wintertime so that you absorb it into your house? Then you need to talk to your glass guy, and you're going to probably pay for it, but you want a solar heat gain coefficient for your south glass that is high, because you want the heat to come through and heat up your mass wall or your floor or something on that.
Isn't it still more efficient to just do it with your income? Doesn't it still work better? Instead of using your glazing to heat that room, isn't it still more efficient?
The question that Jason's asking, isn't it more efficient just to build a really good envelope rather than trying to gain the solar heat through the windows and stuff? Yeah, there's big debates over, where's the best bang for your buck? Because if you try to build, and they're not as popular as they were. Back in the 70s and 80s, there was this big push to build these passive homes, and so they'd have a whole bunch of south-facing glass, and then they'd put a block wall in the middle of the house and paint it dark so the sun would come through and heat up the wall, and then the heat would radiate through the house during the night. Well, as soon as the sun goes down, what happens with all those windows? Massive heat loss through the windows, right? So we have some heat there, but we're losing it so dang fast. And so your question is basically, how about you just build a really good envelope, put in really good HVAC, and it's not going to cost you much.
Well, and also in the summertime, you got all that heat still heating up
Yeah.
that room.
Yeah.
That's where your the position of your windows.
Yeah.
The
sun,
degree of the
yeah.
sun is different.
Yeah.
True.
Yeah, you don't, if you have a little bit of an overhang and it's directly south, you really don't get any sun through it in the summertime.
The sun's too high.
The sun's too high, it's right overhead. But trying to anticipate how it's going to work, and it's like the solar panels. Do you put them on things so they rotate and face the sun exactly? Is it worth that expense? I don't think so.
Even in the summertime, especially down here, some of your evening temperatures are very dropping in the 90s in the middle. So you still have that temperature difference of 25, 30 degrees
At nighttime,
at night. You're still gaining heat from the exterior
all the time.
without the sun being present.
Yeah. Getting your head wrapped around this, getting your head wrapped around the science of heat flow. My first two houses were all brick. So the first house I bought over by Matt was all brick. Then I built my house in '94, it was all brick. And then when I sold it, I bought a house that was siding. Now, my all brick houses, and this is what I was used to, I thought I understood it, but my all brick houses, when it started getting warm in the summertime, the sun comes up in the morning and the sun's beating on the house, and it took a while before my air conditioner would turn on. Why? Because of the mass of the brick. It took a long time for the sun to heat up the brick, and then the brick passed the heat onto the house.
And it held the heat into the heater.
But in the evening, it held the heat, and in fact, you can walk by a brick wall, after it's cooled down outside, you can feel the heat radiating at you. So, so the air conditioner went turn on for a couple of hours after it started getting hot. I moved into a house with siding on it, and as soon as the sun hits the house, the air conditioner turns on because the heat's moving through quicker. It doesn't have that mass slowing down the heat. And so you say, well, but my air conditioner runs later in the night because I had brick, because it keeps radiating heat both ways. Well, that's this key in our Salt Lake City. Then some of that heat starts radiating outside and some of it's still radiating inside. So actually the mass actually is, if you have a climate where you have a high temperature range like we have here, out in Salt Lake, it's more efficient. Down here in Phoenix, it's not quite so efficient because it never cools down.
That's why the passive works for greenhouses, but not necessarily houses.
Exactly. Passive works for greenhouses, but not houses. That's a great statement. Because we want a whole lot more precise comfort and temperature control than a plant does. But a plant, I think, benefits from a little swing. I threw this in because people wanted to know generally what they could expect. And it's in there. Like I say, if you want a full-size set of slides, send me an email. And it gives you what you should expect for a U factor depending on the window, whether it's metal with a thermal break, non-metal, and improved non-metal. And so it talks about the different things. And you can see, these numbers are reasonable with what we've been talking about. And the solar heat gain coefficients has dropped too.
Is there a way for somebody to make their own windows? They just want to do wood frame, build it themselves?
They can.
They gotta make it up other places.
There
is the default table.
Well, you can use the default table, or we're going to do a wall calculation here in a minute, and they can do a calculation, or ASHRAE has a bunch of tables that are a little bit better than the default tables in the code. But generally, if they want to build their own, they can have someone make you the IGU, the insulated glass unit, and then put in the wood frame, and then you can get a certified number. Now, I just want to throw this in because it's slowly coming into the market. My oldest son works in commercial buildings, and this is a building up towards the mouth of Big Cottonwood Canyon, and they have what they call dynamic glass. Dynamic glass, literally there's wires going to every pane of glass, and is controlled by the building management system, the computer that controls the whole building, and it literally darkens the window, increases the reflectivity, or drops the solar heat gain coefficient based on the conditions and how they wanted to set the windows. So the sun is going to be striking this glass, and they can, if they want to, they can darken this one too, but they've chosen not to darken this one, so they give it a little more light through. But This one, see, this is one shade, this is one shade, this is darker, and it's all done by the electronics in the building management system. And what it basically does is changes the solar heat gain coefficient from 0.38 down to 0.09 when it's full dark mode. When it's full dark mode, you can't see through it. Where did this glass first start being used? Multi-million-dollar houses around bathtubs.
We call it smart glass.
You just put in one of those and you go to full dark and you can't see through the window. So you can put it around your big tub. But yeah, this is 4 levels of tint, but it's also what your visible go to. Virtually almost nothing. You get 1% of the visible light through. Kind of interesting, huh? Can you ever pay for it? This building right here, by putting that glass in, when they modeled the building, they were able to decrease the chiller by 60 tons of cooling capacity. So in a commercial building, you can't show a payback on it. Walls. Above grade walls. So we've talked about the fenestration. We all know that the fenestration is poor and we need to get a reasonable number. So how are our walls? Look at all this lumber they're putting in here. Maybe they're carrying a point load up above there, but that's a lot of lumber, isn't it? When you put lots and lots of studs in here, you're decreasing the area you can insulate. However, they have done what here on this corner, California corner, so they can get some insulation in around it. So just your framing practices does change a little bit. How does this little teeny space here get insulated? It better be foam, because packing it with fiberglass, my walls that I just tore apart in my bathroom, I have all these little spaces that are packed with fiberglass, but it isn't cut right. It's like 5 times bigger than it should be, and it's been shoved in with a putty knife or something like that, which is almost ineffective. So those should be foamed. Walls should be built so you can get something in the corner. The corners are always a weak point. So we have above grade walls and we have below grade walls. And we blanket typically our below grade walls if they're unfinished, and we insulate these above grade walls.
Do you get a lot of energy increase by going to 2-foot on center frame?
I can't tell you exactly how much it changes. I've done the calculations before. For everybody, I don't know if any of you are familiar with it, but Construction Instruction, it's a group out of, I think they're out of Denver, aren't they? They have an app for your phone. So, and yeah, I mean, it's a really cool app. And it's a wall calculator. And so you can put in 16-inch centers, 24-inch centers, and put in your insulation values, and it will put in exterior, whether you put sheet foam on the outside or what you do on the inside. And bottom line, what it really,
What the manufacturer does.
yeah, what it will tell you. What do you think the best way to insulate this wall to get the very maximum R value is?
Continuous insulation on the outside.
Continuous on the outside. If you spray foam, this whole cavity full of foam, R7 per inch, that's like R35 somewhere there for the cavity, but you still have all the wood. You're better off putting, you know, 2x6 wall, put an R21 bat in it and putting an inch of foam on the outside, and you'll get a better R value than filling this cavity full of foam. So putting some insulation on the outside does what? It does away with some of that thermal bridging through the wood, where just filling cavities doesn't give you that. But whatever the case, when we're doing our load calculation, we need to know how they're building the wall. If you look at Who's from Summit County, Wasatch County? Something there is.
It was.
You were. You are. What does the prescriptive table say for climate zone 6 and up?
Or
For walls?
continuous
R19 is what
R10.
we go by.
If you look at the prescriptive table, it will say R20 plus 5. And it doesn't give you a cavity only value, right? Isn't that right?
Correct.
So cold climates, the prescriptive table, the code's trying to say, if it's really cold, we don't want you to just rely on cavity insulation. We want you to put some foam on the outside, right? Why?
Now that makes sense, yeah.
We don't want to condensate on the backside of the OSB.
I was having a lot of guys do hybrids. They were doing like a 1-inch foam on the inside plus the continuous on the outside, and then they put load in cellulose against that to keep that foam, the
Yeah.
moisture.
So what we found in Summit County, if you only do 1 inch on the wall,
R5, it's not
you'll
enough.
create a problem. You'll create
It's
more
not
of a
enough.
problem.
That's why they're doing that hybrid.
Or put 2 inches on the outside.
You gotta put 2 inches of foam in the walls. You do 1 inch, you create more problems than yourself.
Yeah. So, anyway, the bottom line is, and I know we're kind of rolling over into what the energy code says you have to do. Bottom line is, when you do a load calculation, you gotta get it accurate. You have to accurately identify how the wall's built. And how it's insulated. So, number 49, we've still got a lot of slides to go, don't we? So let's go back to this sheet. And I'm gonna go through a couple of pages of this right now just to bring everything in context as we move on through the rest of the discussion today. And obviously, if I put the whole sheet on one slide, you can't read it. So I'm taking section views. So we've already seen this part where we talk about our design conditions. And you notice that design temperature difference. So this number and this number are just the difference between these two numbers, right? We subtract the 7 from 74, we get that. We subtract the 73 from 97, we get that. That's our delta T, our temperature difference. What does the daily range mean? That's just what we talked about. You go to Hawaii or San Diego, and the temperature doesn't change 3 or 4 degrees day or night, right? So that's a low range. What do we change here?
Extreme.
We can change 20, 30, 40 degrees between first thing in the morning at sunrise and the middle of the day. So we have a high range, which is good for us because we can catch up, you know. We might get a little behind with the system, we can catch up each day. Our humidity, we're always quite dry, and we talk about moisture, we're always, if we're looking at 50% inside humidity, we're always drier than that. The next line talks about the equipment we might pick. This guy selected this Lennox furnace. It's a 70,000 BTU furnace, 95% efficient, 66,000 BTU input. This is the output. That's plenty of heat. That's a lot of heat.
Now, in regards to the loads about 30,000, but they expect something twice that.
Yeah. Where we really get into a problem is because of our altitude, we need a lot of airflow.
Right.
And furnace manufacturers don't make small furnaces with big blowers. And you can't buy a 40,000 BTU furnace with a big enough blower for the air conditioner. And so they've gone to this 60,000 range to get a big enough blower. And I really like to see them, you know, when they say, oh, I need a bigger blower, and you do need a bigger blower the higher you go because the air is less dense and you need to move a lot of air. Put in multi-stage. Jason?
Can you look at that model number and tell whether that's a 2-stage or not? How do you have to research it, or is there a way to tell?
There's no code in there other than find out what Lennox's code is. And I used to, well, the products that I sold, I could look at them and tell you everything, but I don't know them off the top of my head. The Dominion Energy app gives you specs for just about everything if you can find it. But yeah, a house like this where they're putting this house loses a little bit less capacity. It has less capacity than this because of altitude. It's already going to be 2 to 4% lower than that.
Right, they're derating.
Yeah, for the duration. But still, you're right, it's double what it needs to be.
Right.
Two-stage would be great, but I don't.
I think a lot of.
Our cooling is more, our airflow and cooling is more critical than.
Right.
So that's why.
So Brett, what is the difference between the input and the output on those numbers? Like what?
Sure, that's a great question. There's that many BTUs. When this burns so many cubic feet of gas, there's this many BTUs. 1 cubic foot at sea level has somewhere around 1,000 BTUs in that 1 cubic foot. You burn it at our altitude with our thinner air, the gases that comes out of the pipe expands more because of our thinner air, and we get less BTUs out of a cubic foot. So what do we do with our gas pipe sizing tables? We have to do that correction factor. We do a deration for the gas line, but we do a deration on the furnace too. But let's just say at sea level, we run this furnace, it burns this much gas, this much gets into the house. Where does the extra go? It goes out in the plastic pipe because it's 95%. So this is roughly 5% is thrown away. The 80% furnace throws away 20%. Why does it throw away 20%? Because it needs that 20% heat to carry the products up the B vent. The B vent has to rely on warm temperatures to carry it out through the roof. Back when I started doing HVAC, they were 65% efficient, so we wasted between 35 and 40% of the heat, and it was used to power the vent. Those old furnaces, we vented them with single wall pipe because we had lots of heat to carry it out. An 80% furnace, we put a B vent on the connector to conserve the heat so we can carry it out. So it's just the heat that doesn't make it into your house. Notice on this load, and you've got it in your hand, we've divided out for every room, and so we know, and this is why we want room by room, we know what the load is for heating and for cooling, and what CFM we need in each room to meet that load. So it's really a slick program. I used to print these out and send them out with my guys so that they were aware that there's a reason that I only wanted them to put a 4-inch pipe to this little bathroom. Why does this bathroom say 0?
Internal.
It's internal. The dumbest thing in the whole world is you have an internal bath that has no load, you put a heat run in it, and then you put the thermostat on the hallway wall just this far from the door into the bathroom. Now what happens? The bathroom controls the temperature in the house because even with the register closed, you got heat coming into the bathroom. It comes out the door to the return. There's a thermostat sitting there on the wall, and it shuts off the system. And they say, I have to turn my thermostat up to 78 for my house to be comfortable. Well, that's because your thermostat's probably in the wrong spot, and you're heating an internal room that doesn't need any heat. It's logic when you really think about it, isn't it? So anyway, this is I think a great tool. You know, I've done thousands and thousands of these, and we use them in our duct design. These numbers, we take these numbers, we take them in manual D, calculate our duct system from there. These numbers and these numbers to our manual test. We're not going to talk much about that because it just kind of goes hand in hand with the other two. To pick the right piece of equipment so we can meet those, you know, those calculation results the best we can. And with what the manufacturers make, we simply don't have the ability to get a 40,000 BTU furnace with a big blower. 40,000 BTU furnace is a little narrow furnace and you just can't get that much air movement through it. So we end up going to a wider furnace, a 60,000 BTU that has a bigger blower. And sometimes you have to go to an 80. Now I think Wendy back at Midway, back when she was there, I think if they had a big number like that, she made them put in 2-stage.
Exactly.
Yeah, she said, okay, but I want a 2-stage furnace. And that's reasonable. I mean, if you want to go down that road, you might have to defend it. But. Okay, you'll get, there's a lot of pages in here that you really don't need. This one is a code official. You really don't need this number, but it has some interesting information on it. We have our design conditions again repeated on it. And then we have these little pie charts that shows us where all of our load is. And it tells us, and we have a table here that matches this. It tells us where all of our load's going. And there's our total BTUs. It adds up to 100%, and most of it's in our walls. Now this one was including a humidifier, so if you put in the amount of heat that's going to require for that, infiltration, floors, ceilings, doors, and glazing. If you had a lot of windows in the house, this glazing number would be a bigger percentage of your total load. I wanted to comment on something here that I forgot to mention earlier. On all these design conditions, it talks about infiltration. And the method for infiltration is simplified, which is basically we just go to a table in the book and make some assumptions and decide if the house is tight or loose or semi-tight or average or whatever. And for this one, they assumed the house is semi-tight. And then he said fireplaces are 0. Almost all of the homes that you're going to see, the fireplaces should be 0. Because the gas fireplace that they put in everything nowadays is a direct vent fireplace. It doesn't see the inside environment, so we don't count those. This is talking about fireplaces that are open to the inside of the house. Okay?
I think older gas fireplace or wood fireplace.
Yeah, open hearth fireplace, like your parents have in their house.
Yep.
Wood powered exhaust fan.
Great air exchange.
That's what they are. You know, these houses that his parents and I bought back in the 70s, they were all these little brick ramblers, and every one of them had a brick fireplace or stone fireplace right in the living room. It was a big selling point. And as soon as you fire up your fireplace and run it a few times and walk downstairs and you're going, well, why is that smelling funny? And even that loose, crappy built house couldn't get enough air to satisfy the fireplace, so guess where it found the air? Down the V vent. Straight down anywhere. And it came right down the V vent and sucked all the products of combustion into the house. And it's sucking from your bedrooms and everything, so your living room's hot and your bedrooms are cold because it's sucking combustion air through your bedrooms. So what you had to do is that big window that was right there in the living room, open on the 2 sides, you just crack the window close to the fireplace for combustion air. Because they suck it out. Those are the fireplaces they're talking about here.
And that's the easiest way to sell people when, you know, the Energy Code now wants you to have that high efficiency EPA rated freestanding fireplace, and that's the easiest way to sell them. This is not a spaceship you live in. Atmospheric pressure is going to stay the same. And if you're eating all this air now, or where's it coming from?
Yeah.
And that's why you want that dedicated combustion, new style fireplace, so it eats it directly from the outside rather than sucking it from the windows into the house.
Yeah. Yeah, an open hearth fireplace really doesn't belong in a home built today. It simply doesn't fit. It doesn't work with the code. It doesn't work with how we build the houses. You need a direct vent fireplace just like you need a direct vent furnace and everything else. All this open combustion stuff needs to go away. causing us more problems trying to be cheap and save a few bucks on a furnace or a water heater. And then we have to deal with the consequences of it.
50 years.
Yeah, forever. Cooling, notice that the chart changes a little bit. Look at glazing. Glazing's a much bigger part of cooling. We know why, because we just had that discussion, correct? So this is informational. You don't need it for what you're looking at. This is one of the sheets that I really like to have when I see a load calculation. And I numbered this when I added a number at the top. If you look at the page numbers down here at the bottom, we have like 5 different reports in here and you'll never be able to follow through. But I put a number at the top so you can follow along. Construction components. Now the guy that does the load, he can print one of these for every room in the house and you'll end up with a stack of papers this thick. I really only want to see it for the entire house. But we're talking about walls. Here's a wall. And if you look at this number, 12D-0SW, you go to Manual J, you can go to a table in that book and it will give you this same information right to this number. So by selecting the wall on this house plan, it says we have this wall assembly, which is frame raw with stucco, wood sheathing, R15, half-inch drywall, 2x4, 16 inches on center. North wall, we have 334 square feet. Northeast, we have 15. East, 387, and so on. So here's every wall, the direction it faces, and total it's 210 square feet of wall. And you can pick any one of those and confirm those. Here's the insulation. This is the U times the delta T. Here's our loss. Here's our cooling heat transfer multiplier, and here's our gain. So this is our heat loss and this is our heat gain. This has done that 1 square foot at a time analysis of your building thermal envelope. And you can just verify by going to construction components, does this match what's on the plans? Do they really have R15 listed on the plans? Do they have R15 listed on the res check? What's this wall? 15. This is the basement walls. Same thing, we can verify there. What's a partition wall? What do you think this is for?
The garage in the house is.
On the garage of the house. Partitions are between, it's not outside, but it's a space that's at a different temperature. Your garage is always warmer than outside, unless you leave the door open all the time. Don't make them do this. If they want to call the garage wall outside wall, that's okay. Do some of you have neighbors that leave their garage open all the time? Every time we drive past my previous house, it's only like 1.5 miles from where we live, and we drive by and my wife always looks over. Ken's got the garage door open again. He leaves it open all the time. Well, why is my wife concerned? Because I had a sink in the garage. I had heat in the garage. When he bought the house, he said, well, I'm never going to run that. Well, that's fine, but he leaves the garage door open all the time. I wonder if he shuts the sink off in the winter time.
You may find out eventually it's been on.
He's been there 13, 14 years. He probably
done something then.
done something to it. Anyway, so when you go to construction components, you can see the walls. And we'll go to another slide. We'll look further down on that. Here's CI, continuous insulation. This is what Jason was mentioning. This is a house in Payson area that the insulation company Owens Corning came out and they showed an example of how they recommend you put foam on the outside of the wall.
So I have a question for that. I've never seen the continuous insulation on any of the residential that I've inspected. How are they actually their products to be outside? Whether it's hardboard or vinyl siding, are they just using water staples, things like that?
The products will tell you how much foam you can install over. And it's usually, most of them want to limit it to 2 inches. Now, some of them, some like it, some home design, some architects and some energy specialists like to see you put little strips, sleeper strips or something on it, so that you have a little airspace behind your siding. You know what I mean? But manufacturers have specific, requirements they want for their materials.
And it's important that whether it's a dense board, closed cell or open cell installation too, because that's going to make a determination on the moisture issue.
Whether it's open cell or closed cell. The seams are a big thing. If you're putting foam on the outside, you're using it for your weather barrier, your moisture protection and all that stuff. And really it's a real tight air barrier. But if you put the wrong tape, I found out this the hard way. I put 1.5 inches of polyiso on the back of my house when I was remodeling. I was changing my windows and I had rot coming down all the corners because I had no weather barrier. And so I just tore the siding off the whole thing and I put polyiso on it and I thought, oh, I have some Tyvek tape. So I put some down and guess what? Tyvek tape and a polyiso cyanide expanded and contracted at a different rate, and like within 3 days, the tape had cracked. That's because it wasn't the right tape for insulation. But by doing the tape, it provides the completeness of the weather barrier. You're fine. To qualify as continuous insulation, now let me back up. What's the advantage of this insulation? We don't have the bridging for the lumber, right? So to qualify as continuous, it has to be penetrated only by a fastener. And what do we have? Just fasteners. We can't have a channel or, a strip of wood every 2 feet or something like that that goes all the way through. It's not continuous, then it's cavity. So for continuous insulation, only be penetrated by a fastener, use approved tape. I explained why. Also serves as the air barrier and weather barrier. And as Jason mentioned earlier, and I probably didn't explain this very good, I touched on it. If we look at, let me jump ahead real quick. This one works. Here's a wall with insulation in it. What's the temperature of the inside face of the sheathing when it's cold outside?
So same temperature as outside.
Close to outside, right? So what does that tell us is going to happen?
Condensation.
Going to condensate, just like that did when it had ice in it. And Jason mentioned that they found if you just, in Summit County, if you just put R5, it wasn't sufficient to stop the condensation, that you needed to go to R10 on the outside if you really want to stop the condensation from occurring there. So is that condensation occurring here all over in our communities? It is. It really is. And maybe it just occurs for a few hours and then it will dry back out. But maybe it won't. So what do we do? We need to first make sure we ventilate the excess moisture out of our house. That's the most critical thing. Now you might say, well, our vapor barrier is going to stop it from getting there, but our vapor barriers don't, because we have all the holes cut in it with all of our outlets and everything else. So the moisture is going to get in there. That's kind of a little side note, but it's part of our load calculation, what we're talking about. We need to make sure we represent the house the way it's been built. We all know that this is actually exaggerating a little bit. There's more insulation there than we really get there with standard trusses. And if this is a bathtub right here, you know you're always going to be fighting mildew and stuff growing right there because it's always so cold there. So there's foam on the outside. I expect that we are, I don't know how many years, more and more, we're going to see more and more foam on the exterior. A lot of homes up in the north, Alaska and Canada and stuff like that, they're putting all the insulation on the outside and they're not even putting anything in the cavity. They're doing 4 and 6 inches of foam on the outside. And what's another method to build a wall, and I don't have a slide in here? ICFs. Insulated concrete forms. That's really for a wall. How do you beat insulated concrete form wall? Great insulation. We're not going to condense, and even if we had some condensation, which is not going to occur, what's it going to condense in? Concrete. But as long as we're wood framing, and I don't think that's going to go away, we're going to have to move more and more towards putting foam on the outside. Down here, they do some of it just with their stucco systems. But maybe they need a little bit more, and maybe they need to upgrade their insulation from expanded to extruded or polyiso. That's where they get some serious R value out of it. So let's talk, we talked about a window, let's talk about a wall real quick. I have an 8 foot by 12 foot wall, so it's 96 square feet. Now here's the long way without manual J, where you calculate each one individually. Here's our wall, and I'm not taking into account the studs in this wall. Just for our discussion, this is a wall with sheathing, insulation, and drywall. So we have an outside air film that's clinging to the wall that gives us an R.17. We have siding, our sheathing and everything gives us 1. So a 1/2 inch of sheathing is about 0.5, and then whatever our siding product might give us another 0.5. R11 in a cavity, drywall, and an inside air film that gives us a R13.8. One of the reasons I put this slide in here is every so often someone will give you a document, whether it's a res check or a load calculation, and they'll say, well, the wall is R11 or R13, and then they add these other numbers in on top of it. Then they add in the drywall, they add in the sheathing. When you pick an assembly out of res check, or you pick an assembly out of Ride Soft or Elite software, and you say a 2x4 wall, 16-inch centers, it is already accounted for all this stuff. You can't add it back in again. It's already done. People will try to do this to get a res check to pass. They'll say, well, it's got R11 in a cavity, and then it'll say it'll add up this number, this number, this number, and this number, and say we have R2.8 continuous insulation. Well, that has already been accounted for when they picked that assembly.
You still seeing, I haven't seen that for a few years.
I get a call every 3 or 4 months where someone sends me a res check that.
Probably when I need to hear about it.
And so that comes up with this number, but we have to take and throw the studs and everything in if we want to calculate real close. For our discussion, we have an R13.58. U equals 1 over R. So the U for this wall is 0.07, blah, blah, blah. So 0.74 is our U. Our temperature difference, we're going to call it 65 degrees. So we just do our math. With our 96 square feet, our U, our temperature difference, and that wall has 462 BTUs going through it. Our heat transfer multiplier, our U times our T, is expressed in BTUs per square foot, so we just have to multiply by the square footage to get the number. So our walls are pretty good even at R11. They're better than our windows by quite a bit. Ceilings. Okay, I just talked about continuous insulation. I blow attic insulation in a trussed roof. Do I count the first 3.5 inches is in cavity and then the rest of it that's on top continuous because it's rolling over the top? No.
See that all the time.
You still have.
See it all the time still, don't you?
Yeah.
When you pick it in Right Soft or you pick it in Res Check or anything else, if it's a truss roof, it's going to assume that you have these intermediate cords on your trusses and they're going to penetrate your insulation. It's more than a fastener, and you don't count that additional insulation on top as continuous. And in fact, you take a thermal camera and look at a truss roof, and you can see where every place those framing members come down and contact the bottom cord of the truss.
You can see it with the frost.
Huh?
You can see it with the frost.
Yeah, you see it with frost too, huh? Especially if it's metal trusses.
Brent, on an exterior wall, would you have that same issue with direct vents coming out, dryer vents coming out, plumbing spigot coming out to break up that continuous wall?
And the question is, what about all the penetrations you have in your outside wall? Well, we don't have a lot of them. We have a few, and we're just going to assume there's a few of them. But what's the key thing we need to do to those? We need to more just seal them at the surface. Where should the sealing take place? Where your air barrier is, back inside the wall. So it really needs to be, if we are using the outside with our weather screed, we need to make sure that's sealed. And if we're using the drywall on the inside as an air barrier, then we need to make sure all those penetrations are sealed. So we just need to make sure that it's, whatever we're doing, it's continuous. But we have to assume that there's going to be a few penetrations, and we don't. They're not going to make a big enough impact to really worry about them. I was at this slide a little earlier. The code as written assumes that this is what's taking place, and Right Soft and Elite and the other softwares also assume that if it's a standard truss roof, that our insulation is going to be reduced around the edge. They do have options to select high heel trusses where you have full depth insulation all the way out, which is a much better system, but you just need to account for it. Now, if someone just picks standard trusses, not raised heel trusses, don't send the load back. It's not going to be big enough to change the load. And make sure that they have the right truss selected. I wouldn't send it back and have them redo it, maybe warn them about it. But
On the Res Check or manual J&D?
On your manual J&D. If they do this, the energy code actually allows you to drop the attic insulation from 49 down to 38. I imagine the 21 code, which goes to 60 in a lot of our climate zones, lets it drop to drop one level.
Is an R60 about as good as it gets, like real world?
The question is an R60 about as good as it gets? My opinion really is R49 probably, going from 49 to 60 really isn't giving you enough benefit.
Maybe 1%. We did a study in Colorado on it, and because we was concerned about recess camps.
Yeah.
What the penetration is. We was an R48, and they wanted to go to R60. One jurisdiction did. We did a study on it, had a complete analysis done, and it turned out it was a difference of 0.1%.
It's not very much. And I mean, if the state were to amend that back to 49, I wouldn't resist it. You know what I mean? It's, we'll get, hopefully I have another slide in here that we can look at this and we can see. You know what? I'm going to jump back real quick. Remember where we were. Ceiling. So, and I don't remember what the attic was, but it's 2,300 BTUs. If you double the attic insulation, let's say this is R38, if you took it to R76, you would only drop this number in half. It's already a relatively small number, right?
Your ceiling was a 38.
It's R38. So by taking it to 60, we're only going to drop the number.
And what you gotta do to get that with your numbers and everything
Yeah.
else.
You know, the high yield truss does way, way more than adding the extra insulation. I think rather than go to R60, they should have said in climate zones 5 and up,
You have to
do high heel trusses. That's much more bang for the buck. And I'm sure studies and stuff will show that. But you need to put it, whatever, you need to calculate what you have. And that's the, you know, it's hard to talk about just load calculation without talking about the energy efficiency. We don't want to compress insulation. So ceilings, I went all the way back and it was the next slide. R38, the heat transfer multiplier is this, and we just really don't change that much. So like I say, to double that insulation, we're only going to cut this in half. And that's the difference of, you know, 10 square feet of glass or something like that. You know, it's just not that much difference. So this is again page 4 or 5. It's page 4. This shows our ceiling. And it's just a pretty small number when you look at the whole thing. Let's talk real quick about ceilings without attic spaces. Again, we need to input this into our load calculation correctly. But I need to caution you, if you're not aware of this, roof decks condensate much worse than walls. I mean, they really do. And our attic ventilation sucks, I'll tell you that right now. That aluminum soffit with the little perforations in hardly let any air into your attic. I bet 80 to 90% of our attics right now are way short on sufficient air to ventilate them. But if you don't ventilate an attic, if it's unvented, what are they doing here? They're spraying foam on the inside to stop the condensation. In climate zone 5, this Wasatch Front down in the valley has to be R20. If you're in climate zone 6, it has to be R25. This isn't in the energy code. This is in chapter 8 of the IRC. And so if you're not catching that, you know, roofers come to re-roof a house. What's the first thing they do? They walk across the whole roof and find the soft spots for all the places that the sheathing's gone to heck because of all the moisture that's condensed on it.
So what should the thickness of that closed cell foam be then?
R20, which is 3 inches,
So it needs to be at least 3 inches.
and R25 if you're in climate zone 6. Or you can put it on top. This is a nice roof system, but it's going to cost you some serious money to build it, where you put several layers of foam and then you resheathe the roof again. And there's systems where you can ventilate that above the space, but
So if it sits down on the.
it's like it sits.
Yeah.
Yeah.
I see that a lot in my higher altitudes, like up in Brian Head, where we're, you know, not between 9,000 and 10,000 feet. Yeah, they have to do the cold roof, because if they don't do the cold roof, the snow will actually rip whatever roofing material on that roof off that roof.
Because of the ice dams.
Yeah, and some of the roofing manufacturers require you to do that.
Yeah. This is, you know, and this is the kind of building science of it. What happens with, I think this is worth discussion. Yeah, I had it right on the slide. What happens? Almost no insulation here. We have this heat coming up It melts the snow here. We have heat coming through. It melts the snow up here. R60 is kind of the magic number that ice dams go away, but you have to have R60 all the way out to here. So if we have heat going through, we're going to get some melting of snow, especially right here. What happens when the water gets down here? It freezes. And it literally is an ice dam. You guys have seen them. So you build up this big, huge pile of ice. And what does it do? It just keeps getting bigger and bigger, right? And it's tied to the,
Yeah, it takes that metal sheet roofing material.
it takes
right
and
off the
pulls it right off the roof. Ice is heavy. You have tons and tons of ice hanging off the eave of a big overhang, and it'll tear everything off. These things all cost money. This costs money, and if you do this and you ventilate it, so you put a 2x sleeper, then you're golden. You'll hold the snow. It'll be even. It'll never be melting, and everything works great.
So just for clarification for me, when I'm having them do it, if you've got a ceiling system and it's just TJI, you've got your roof on top, sheetrock underneath, and just TGI, roof system. You want to spray that with foam underneath against the roof decking. How thick? And then the rest is insulation.
3 inches in closed cell.
Well, so it's got to be 3.
In climate zone
Where you
5.
at?
Where you at?
Yeah.
3 inches.
So you gotta get an R20.
So it's got to be 3 inches of
You-
close,
you-
and then the rest.
Whatever, it has to be R20.
It has to be an R20.
So you got to talk to your foam guy.
And then the rest of that cavity gets filled with
Whatever.
that or whatever they
Yep.
want.
Hybrid system.
Yep.
Yeah.
If you go to this section and read through it, it's a little confusing at first, but basically, you study it out, it's basically telling you, you have to have a certain amount of air impermeable insulation to prevent that condensation.
You know,
Right.
I just fought with the guy that done blown-in cellulose. And he drug this fight out for like 4 months. And finally ended up ripping it all out.
Yeah. It's not that it's in the code, it's the science of thermodynamics and psychrometrics, right?
Well, it is in the code. It's just not in the energy code.
Yeah. Yeah.
To make it work.
If we want it to work, I mean, we can argue about, and the code might not be 100% correct in some places, but it's still, psychrometrics is the study of moisture.
And you can do like like Summit County would allow blown-in fiberglass if you get a certain density. But there was a lot of science that went into that.
Yeah. Well, there's, they call it, I can't remember what they call it, but there's a name for it. There's some professionals, some engineers that came up with this process where they investigate and they calculate based on all those conditions, and then they will approve a smart membrane.
Yep, smart membrane.
A smart membrane with just blown insulation. The problem, and some of you might have seen this, it's called Membrane. It's one of the brands. And it's like a vapor barrier that'll let it dry, but it won't let moisture back into it. But the problem is, for it to work, it has to be 100% sealed. How do you maintain 100% sealed membrane on a ceiling without the drywallers cutting holes in it?
Install it yourself.
Well, and the big problem is the can lights.
And the can lights.
That
The can lights are called airtight, but are they really airtight? No, they let moisture through. They have a certain leakage rate. At the county, we let a few do it, and then we studied a little bit deeper. We had some problems. We said, no smart membranes, because no one will install it correctly and maintain the integrity of it. So, anyway, on our load calculations, we need to account for it. Floors. We see these a lot. How many see homes that are built with garages with a washroom over it? Tons and tons, right?
Yeah.
How many do you hear, and I know they don't all call you the jurisdiction all the time, but how many of those rooms do you think have heating and cooling problems? Almost all of them.
So, my permit catch, she said, oh, our bonus room is horrible, we've gotta get in there and re-insulate it. No, I think you need to do your heating and air conditioning system.
It's a good spot for a mini split.
It's both. One of the big things, and this is a garage, and I didn't put in all the slides I have in my energy code class, but they had so many problems with them, and they have ductwork that are going out in them and all this stuff, that they net and blow all of them. And where they have fur downs for ductwork and everything, you go in and try to put bad insulation around that, you have all these air spaces above that it basically makes your insulation ineffective. And so if you have those cavities, they just need to be full of insulation. And this helps a lot, but we need to account for it. I'm a big fan of blown in insulation, because I don't think anybody ever installs insulation bats correctly. They never split it, they never cut it around wires, they never cut it around boxes or anything. But our floors, we need to account for those rooms over unconditioned spaces, our cantilevers, our rooms above garages, our slab on grade. We got to address the slab edge.
Years ago, they were fighting over the insulation and how far in and all that kind of stuff, and how much for under slab. Asher was fighting, everybody was fighting over it. Did they ever resolve that?
I don't think.
They were fighting science back and forth, and how much migration of thermal was getting back, and then how much they were getting out for moisture and everything.
So the question is about slab edge insulation. And there has been a lot of fighting, and really what it boils down to, if it does not come to top a slab, it doesn't work. And commercial people, and ASHRAE even fought this a lot. They wanted to bring this slab edge insulation. They wanted to bring the slab edge insulation up to the bottom of slab, and then they said, well, we'll just run in a ways.
Yeah, and then 5 feet, yeah.
5 feet or something like that. Well, you still have this top of the slab that's communicating, and or the stem wall or whatever. And so if slab edge insulation doesn't come to top of slab, it doesn't do any good. You have to break, you have to have the thermal break. Quick note on that. If you've looked at a res check lately, and if it has slab edge insulation, it tells you you have to put slab edge insulation in per the prescriptive table. Has anybody seen that?
I just got to
Yes,
recently
it's
see
a
it.
red line.
It's a red line. It's a box.
It says no trade-offs.
There's no trade-off on slab edge insulation. And that's, res check has been, I don't know if DOE, Pacific Northwest National Labs, when they caught it, but the trade-off requirement or allowance in the code, the UA trade-off, which is res check, is based on the U factor table, which doesn't have slab edge insulation in it. And so they finally fixed it, and maybe it'll get fixed in the 24 code, because you have to now, you can't trade it off with res check. You have to do slab edge insulation in climate zones 4 and up. So anyway, but we have to account for whatever's there. On the load calculation, it might be for an existing house, so we do it how the existing house is built. Basement floors, if you're insulating the basement, now when I'm saying basement floor, I'm talking about the slab in the basement. Our load calculation will actually assign a value to it. Res check doesn't require it. The energy code doesn't require insulation under a basement floor slab. But we do in our load calculation, put in a little number for the basement floor. And so here's a basement floor, 1,600 square feet, and we have a little bit of loss to it. Why? Because it's 50 degrees underneath the basement floor. Here's over a cantilever, 13 square feet of a cantilever. So here's our floor. Now, if this had a bonus room over a garage, we'd have a big number there. While we're on the bonus room over a garage, they really need their own system if they're really gonna be comfortable. We look at the whole rest of the house and we might have 1 or 2 walls exposed to outside, maybe a ceiling. What do we have with the bonus room over at garage? We're exposed all the way around. How can we expect it to heat the same as the rest of the house? Now, we can't, as inspectors say, oh, you have to put a separate system in there. They insulate it the best they can. They make sure they have a return path back and it's gonna be reasonable, but it's never gonna be as comfortable as they might want it to be.
Well, never even close unless it's multi-zone or separate, like mini split or something.
Yeah. The only, summertime's really gonna be hard. Wintertime, if you have an open door, the heat rises up there and it might be okay. So here's the duct systems in the garage I was talking about earlier. So I took pictures. So let's, as we're looking at our load calculation, how we input everything, here's this ductwork inside this fur down. If they come in and they put bad insulation here under all of these, we don't have any insulation above the studs, do we? And are they insulating the inside face of this piece of the fur down? No. And then we have all that airspace above, right? And we have the pipes. Now this return panning, they set it up so it was up 2 or 3 inches. You see how they have it stepped up? So do we make them insulate the duct, or can we allow them to encapsulate the duct in our insulation? If they can get R8 or better underneath it, and they blow the whole thing full, I'd be comfortable with that. And when they blow it full with high density fiberglass, they're gonna get more than R8 underneath it. And when they fill it all up above, all those cavities, then it's really encapsulated. We don't have any of this air flowing around. And in fact, the 21 code actually talks about this option. Blown in insulations around R4 per inch. So if we have at least 2 inches, this one we have much better than that. And this is ones they decided that that's how they're going to do it. That's a good system, and you'll have a reasonably comfortable room above there because you're just not going to have that much heat loss. Bottom line, I would not accept that without, if they're going to bat it, they have to wrap the duct. If they're going to, or spray foam on it or something like that, if they do this, I think that complies with the code.
What's the minimum insulation for underneath that pan? Because a lot of times you don't see them step it up into the, like they gave you a couple inches, a lot of times they just nail it to the bottom of that.
Well, it depends on which section of the code you want to go to. Minimum, a garage you could call like a crawl space, and it could be R6, but R6 or R8 still sucks compared to what we really should have around our ductwork. But yeah, your panning should have it insulated inside or something. But we need to account for it in our load. Okay, this one was in northern Utah. I'm not going to say which jurisdiction it was in, but I received a call that came down through the Office of Energy Development to me. A homeowner was really cold in his house. The furnace was at one end of the house. It had a crawl space. And this jurisdiction obviously doesn't enforce the energy code because they tried to do a conditioned crawl space by insulating the walls. And do we have a problem? Does this insulation do anything?
No, I hope that they just missed it instead of they totally missed the point of what.
This actually, this is the house was done and he was living in it. And
right, but
they added the fiberglass later on. The house was built without nothing,
Nothing.
And so they start talking about it, and the inspector says, well, maybe you better insulate the walls. And now if you're gonna encapsulate the crawl space, you gotta make sure your vapor barrier and everything is perfect down there. But anyway, You can do a crawl space, insulated walls, or you can insulate the floor. In any case, you need to account for it in your load. We could spend an hour talking about this case. This was a long house, big rambler. Furnace was in the garage at the far end. How much warm air made it to the other end of the house and that sheet metal duct sitting in it? None.
Just a quick scenario, say you take out the vents and it looks to me like you got a heat run right there. Could you consider that conditioned space if, since you got a heat vent, say if you took out the air things, right, like that?
If you made this a truly conditioned crawl space, the ductwork's fine.
Right.
It's in a conditioned space. The vapor barrier on the ground has to be taped and sealed 6 mil or heavier, has to come up the foundation wall, be sealed to the wall, and the rim joist, in any case, should have been spray foam.
Right.
Because they will rot. They are gonna mold and mildew like crazy. I don't care what you do.
But you've also got to dump the heat duct in there.
You need to make sure that we have some circulation in there. You need a little bit of heat. And then they really want you to return it into the house, so a transfer drill into the house. But you can't, I had one, and I'm not gonna say where it was, but, and I was called out there as an expert on it, because he was wanting to know if he should sue them. But they cut a little supply into the, it was a crawl space with a horizontal, furnace sitting horizontal, and they had a supply grill register on the plenum on one side and 5 feet over on the other side, they had a return. So it went, it has to cross ventilate the crawl space. If you do this, if the vapor barrier isn't good on the ground, you are gonna have moisture problems because there's always moisture coming out of the ground.
But even if you do all that, isn't it that return air still going to stink, right? It's always going to.
If it's sealed up real well, I mean, Bill in Moab, Grand County, he requires the vapor barrier and then he calls it a rat slab. He requires a slab of concrete. And if you do that, it doesn't smell, it doesn't,
Sure.
you know, and that's just to protect the slab, I mean, the vapor barrier. But whatever, we got to account for it on our load calculation. We got to account for our infiltration. It's almost lunchtime. We really need to be watching our cantilevers. And if I do an energy class, we really go into detail on that. But we have to look at that. How many little holes make a large hole? We talked a little bit. Wind makes a difference on our infiltration. You know, we might think our house is fairly tight, then the wind blows and it just blows the air right through the house. Something else that increases infiltration is we have a poor HVAC system where we don't have a return path. So if you install a house, this house right here, here's our floor plan back here on page 18. Here's the floor plan of the house, and I know it's simplified, but if we have all these bedrooms with doors closed and no return path back, and we blow supply air into the bedrooms and the carpet fits pretty close to the bottom of the door, are we going to positive pressure the rooms? Yeah, we are. What's it going to do? It's going to increase our air leakage and we're going to push air outside. So infiltration is the uncontrolled leakage of air in and out of our house, and part of the good load calculation is ensuring that we have a balance or a good duct system, a good return path, so we don't pressurize or depressurize part of our houses and increase our load.
Well, a good return path will also increase the comfort of the house.
Much. Yeah, completely. And we'll talk a little bit more about that in a minute. If we leak air out of our house, it has to be replaced with air that leaks back in. We can't take air out of the house without replacing it someplace. And so that applies to both controlled and uncontrolled leakage. Controlled is ventilation, uncontrolled is infiltration or leakage. So how do we decide our infiltration? I talked earlier about the simplified approach, and what we simply can do is go to Manual J, table 5A, and it tells you if your house is tight, 900 square feet or less, we're gonna have about 2.21 air changes per hour of leakage, just normal leakage through our house. And the bigger the house goes, the lower the air changes, just because so much of the volume is inside and not at the outside walls. If it's semi-tight, if it's loose, here's our air changes per hour based on force. That's for heating and this is for cooling. So you take a 1,500 square foot house that's average and it has 0.38 air changes per hour, or a 2,000 to 3,000 square foot house, it's going to have somewhere around 0.32 air changes per hour. That's basically every 3 hours you leak a whole volume of the house outside, right? If you leak a third of the air in the house every hour, in 3 hours you leak the whole house worth. That's why we need to account for air leakage, and we account for it in our load calculation because why? We have to recondition, we have to heat or cool the air that comes into the house, the replacement air, right? Whether it's by leakage or by ventilation. And there's tables. This is single story. There's tables for townhouses, there's tables for apartments, there's tables for all different. And this, we're making some assumptions. And I'm not going to read this through. And I think it's kind of funny. The code does this too, but this is from Manual J. It talks about a tight house, talks about an average house, and it talks about a loose house. Most of what we are seeing today is semi-tight. An average house might have open combustion air. Does. A tight house will not, or we have the house sealed. So the person that does the load calculation makes a decision on the quality of the construction of the house, and he picks one of these 5 things. If he says it's loose or semi-loose or average, he's trying to scam you and get a bigger unit because he doesn't trust the load calculation. And so he's trying to get extra. We should not have an average house built today. The code requirements should put it up in this area. So, and here's where we find infiltration. It's on, this is on page 6. If you go to page 6, I left a lot of stuff out, but this is what you'll find on it. This house is semi-tight. And in heating, we're going to leak about 56 CFM, and in cooling, we're going to leak about 56 CFM and 29 CFM. Based on these air change numbers, anybody want to guess why we have more air changes for heating than we do for cooling?
Because hot air rises and so it's going out through the skin.
Hot air rises. So when we have a house in heating mode, we're heating the air, and compared to outside, it's warmer and it's always rising. And the taller the house, the more it does it. And so the heat rises and it leaks out of the ceiling at a greater rate than when we're in cooling mode, where the cool air is tending to fall. And so we leak more through the roof when we're heating than we do when we're cooling. So you're going to have a higher leakage rate in the wintertime. We're going to talk about internal gains here, and then we'll break for lunch. I think that's what we're supposed to do, right?
Yeah, let's break.
Huh?
You can break now.
Let me just hit this slide real quick. I talked about internal gains a little bit right at the first. In the summertime, we need to worry about people, miscellaneous equipment, computers, whatever. We need to worry about lighting, anything that generates heat inside the house, and we have to account for it. We don't count it in the winter time because we can't count on it always being there. We would never want to include that or solar gain in our house, in our load calculation. Do we have any solar gain on the coldest time of the day? In the winter time? When's the coldest time of the day in the winter time? Right at sunrise. We don't have any sun on the house, so we want to account for the actual conditions. What about sun on the house on the hottest time of the day? Yeah, because we have sun on the house and we have activity in the house, and so we account for current gains there. And here's all those. We don't include every light bulb, we don't include every appliance, and we don't include 30 people for Thanksgiving. And as you said, justify it.